In this second part of the lecture, we'll be applying some of the ideas from part one, using the Juno and Cassini spacecraft to explore the atmospheres of Jupiter and Saturn, to understand how atmospheric structure, circulation, chemistry, and meteorology all combine to shape these archetypal giant planet worlds. We'll also try to look at the future of exploration of Jupiter and Saturn. Now, the basic building blocks of a giant planet are the most common elements in the universe. Hydrogen and helium dominate the abundance of Jupiter and Saturn, but these are mixed in with trace elements: carbon, oxygen, nitrogen, sulfur, phosphorus, and various others that are present, locked away deep down within the heart of Jupiter. Now, reducing chemistry in the presence of all that hydrogen means that you don't see the elements by themselves, you see them combined in the form of molecules. And those molecules are the volatile species. These are the ones that condense to form clouds: methane, ammonia, hydrogen sulfide, and water. You don't have to worry so much about methane condensing on Jupiter and Saturn, because the temperatures never get cold enough for methane ice clouds to actually form. However, on Uranus and Neptune, you do have methane ice clouds forming, and that contributes to the bluish, greenish haze colours that you see when you look at those worlds through a telescope. Now, those volatiles will then condense to form the cloud decks, and in fact, they will condense at particular altitudes where the pressure of the gas exceeds the saturation vapor pressure. So what you have are cloud decks of ammonia ice at the topmost level. Then you have a cloud that's actually formed of ammonia and hydrogen sulfide combining to form a solid called ammonium hydrosulfide, below which is a water cloud forming at room temperature, so same sorts of temperatures that we would experience every day here on Earth. Now, when you have water clouds condensing, you're also able to get lightning strikes occurring, and the presence of lightning on Jupiter and Saturn has been measured in the past and will be important when we start to talk about the circulation and dynamics of these planetary atmospheres. Now, I mentioned that methane wasn't condensing within the atmospheres of Jupiter and Saturn, but methane does play a crucial role in the temperature structure and the chemistry of these atmospheres, because ultraviolet photons from the sun can split the methane molecule apart and allow the radicals to then recombine in chains of long hydrocarbons, the most common of which are ethane and acetylene. But we've detected a plethora of higher order hydrocarbons in the upper atmospheres of these giant planets, who are all interacting in complex ways to form a soup of photochemical species within the upper atmospheres. And some of those photochemicals can then go on to condense to form wispy, thin, tenuous haze layers within the stratosphere, and can even sink down through the atmosphere to coat the ammonia ice layers that we believe to be present down in the troposphere itself. So photochemistry is a vital part of understanding the regions of the atmosphere that we can see. Now, this doesn't happen in isolation. Incoming micrometeorites, sometimes large cometary impactors, or just the steady influx of material from the rings and the satellites can contribute exogenic and oxygenated species to the upper atmosphere. So when that gets split apart and interacts with the radicals from the methane having been split apart, you actually make the photochemistry even more complicated with the influence of external species. Now, if the photochemistry and the external influences weren't enough, you also have to think about dynamics redistributing all of your materials from place to place. And here's where disequilibrium species become important. These are materials that should be locked away down at great depths within the interiors of these giant planets, but in fact are brought upwards by powerful overturning circulation patterns, brought up to the level that we can detect them with our remote sensing investigations. So with these different chemical pathways in mind, let's look at the vertical structure of these planetary atmospheres. Now, the troposphere is where the clouds are forming. So naturally, that should be our starting point, because that's what you see if you look through a telescope at the atmospheres of Jupiter and Saturn. You see the banded structure, which is the condensate clouds forming in different patterns. And as I mentioned at the beginning, you have a topmost level of ammonia ice clouds and a water ice cloud at deeper levels, which is powering some of that convective motion. The troposphere is the region where the temperature is decreasing with altitude, but at a certain level that we call the tropopause, the influence of all of that methane gas absorbing energy from the sun is such that the temperatures actually begin to rise again. This is the stably stratified region of the atmosphere that we call the stratosphere. And you might hear the stratosphere and the upper troposphere sometimes referred to as the middle atmosphere, separating the deeper convective region from the more tenuous upper atmosphere where external influences might be important. As we move up from the stratosphere, we don't necessarily have strong evidence for a mesosphere like we have here on Earth, but we do transition into the thermosphere. And here's where the influence of ionization of the atmosphere can become important, because that ionization can lead to the ability of the atmosphere to conduct, for currents to flow through the atmosphere, and can lead to further heating of the atmosphere, meaning that the thermosphere just gets warmer and warmer up to the external environment of these planetary systems. Now, all of the convection, all of the weather, if you like, that we observe within the giant planets is taking place within the troposphere, but that may be being influenced by motions which are occurring deeper down within the interior of these worlds. Now, by interior, that betrays a whole host of complexities that I won't get into here, but we may have fluffy cores of rocky material down at great depths, the metallic hydrogen and helium layers, which are obviously conducting, and then we have a deep troposphere where all the gases should be fairly well mixed by the overturning circulations. But those overturning circulations might then be influencing the base of the water cloud and leading to all of the circulation patterns that we see. So let's remind you that photochemistry is happening in the middle and upper atmosphere, condensation chemistry is happening within the troposphere, and thermochemistry, which is that reducing chemistry forming the key molecules of interest for Jupiter and Saturn, are happening deeper down. And we might further refer to those as the radiative layers, the weather layer, and then the deeper dry layers down at depths below the water cloud. Now, the most obvious thing that you notice when you look at Jupiter and Saturn are those beautiful striped appearances where different coloured clouds, which are also betraying different types of temperature and composition, kept well segregated from each other by jet streams on the edges of those bands. And you can see the jet streams in this little Cassini movie from 20 years ago that shows the jets whizzing along from west to east and quite obviously separating whiter cloud material near the equator from darker material in the northern and southern equatorial belts. Now, these belts and zones are regions of upwelling and downwelling motions. A zone is region of upwelling, and a belt is a region of subsidence. But we'll get into more details of that slightly later on. To begin with, though, I want to make you think about terrestrial meteorology, where we do have a similar banded structure to the circulations of the atmosphere and indeed of the oceans as well. At the tropics, you have a Hadley circulation where the air rises over the equator. As it moves towards the higher latitudes, it has to conserve angular momentum, which means you get the formation of the subtropical jet streams to the north and south of the equator. As the air then falls again, it's also feeling the Coriolis effect. It has to conserve angular momentum, and it actually then moves slightly towards the west. And this is the formation of the trade winds that would have taken early sailors across the Atlantic from east to west. Now, that circulation pattern at low latitudes then gives way to a slightly different type of circulation at mid latitudes, the Ferrel cells. And here you have a overturning circulation in the opposite sense. We believe it's driven by the interaction of small scale eddies, which then transport their energy upwards into the larger scale zonal flows. But the key thing to think about here is that you have low latitude Hadley-like circulation patterns and mid-latitude ferrule-like circulation patterns. And as we'll see in a moment's time, there is evidence for both of those types of circulation patterns occurring within the giant planets Jupiter and Saturn. So this diagram gives you some evidence of those Hadley circulation patterns for Jupiter on the left and for Saturn on the right. The top plots are contours of temperatures. And what you can see is that the equators are colder than the neighboring north and south equatorial belts. The equators would be cold if you have rising air expanding adiabatically. And as you expand a gas, it will cool, the temperature will drop. As the temperature drops, you'll start to condense out all of the gases that are present to form those reflective white cloud decks that we see. As the air then moves to higher latitudes and begins to sink, as it sinks, it warms adiabatically. As it warms, it re-evaporates all of the condensed aerosols, and you see the darker coloured north and south equatorial belts. So temperature is a key element of what we're talking about here. The lower plots show our estimates of the distribution of ammonia gas. And remember I said that ammonia was one of the key volatiles, the key condensing species within the atmospheres of Jupiter and Saturn. And for a long time, we've known that the equators are enriched in ammonia, whereas the north and south equatorial belts are depleted in ammonia. And this is again consistent with rising motion at the equator and sinking motion over the north and south equatorial belts. And we have evidence for both Jupiter on the left and Saturn on the right. The Juno spacecraft carries a microwave remote sensing instrument. The key thing about that is that it's able to get much deeper down than we've ever been able to get before to look at the distribution of ammonia gas. And what it revealed shortly after its arrival at Jupiter, in fact, was that the enhanced ammonia gas at the equator and the depleted ammonia gas at the north and south equatorial belts it extends extremely deep, down to 60 or 70 bars or so before you start to get to a region where ammonia is well mixed. So much deeper, in fact, than we expected, and we'll come back to that later. But the key thing from this slide is to take away that there is evidence for Hadley-like circulation patterns at the low latitudes of Jupiter and Saturn. What happens then if we go to slightly higher latitudes? If we look at the temperature field of Jupiter on the left and Saturn on the right, we can see that these belt zone contrasts in temperature are present at all latitudes, all the way up to, say, 60 or 70 degrees latitude or so. We also see that the peaks of the zonal wind field that I've denoted here as vertical dotted line are well correlated with regions where the temperature is changing extremely rapidly, where the gradient of temperature as you go from south to north is at its maximum. Now, why would that be the case? There is a basic principle of planetary atmospheric dynamics called the thermal wind equation, and it underpins a lot of the discussion of circulation patterns within these giant planets. And what it says is that a vertical shear on the zonal winds, that is a change in the velocity of the zonal winds as a function of height, is in balance with a gradient in the temperature as a function of latitude. In this case, in the equation on the right, I'm using y to denote north-south distance and z to denote up-down distance, so vertical distance there. That balance between the vertical shear on the winds and the gradients of temperature is played out on the diagrams that you have in front of you here, where the jet streams are located at the regions where the temperature gradients are maximum. The implication of this for the upper troposphere of Jupiter and Saturn is that the winds we see at the cloud deck, as measured in those lower panels, decay with altitude as you go higher and higher. They get weaker and weaker as we go upwards. Now, we don't actually know why that is the case. We just know that the temperatures and wind gradients are in balance with one another. We'll come back to that in a moment. These circulation patterns have been likened to ferrule-like circulations on the Earth, in that it is small-scale eddies and little storms and vortices that are driving their energy upwards into the larger scale zonal flows represented by the belts and zones. So let's draw a cartoon that tries to represent some of what we've just said. We said that in the upper troposphere, the zones are cold The neighbouring belts are hot, and that's as a consequence of rising air over the zones and subsiding air over the belts. That produces a temperature gradient, and the temperature gradient must be in balance with the vertical shear on the zonal winds. And so the green lines, which denote eastward jets, and the orange line, which denote westward jets, they must both be decaying with altitude as you go higher and higher in the troposphere. And this is the picture that we sometimes refer to as the classical picture of belt zone circulation on Jupiter and on Saturn. But evidence from Juno, Galileo, and Cassini started to piece together properties of the circulation below the cloud decks. And what they found was that some of the results are the complete opposite of what you'd expect if you assume this classical view of atmospheric circulation. So what's going on? What's happening below the clouds of Jupiter and Saturn? Well, to start with, we detected those lightning strikes associated with water condensation. So water, ice, the condensation of water to produce ices also leads to the separation of charges. The charges can then reconnect via powerful lightning bolts that can be heard as a crackle by radio detectors on the spacecraft, and in some cases, such as that shown from Baines et al. 2007, can actually be seen as optical flashes illuminating the clouds from below. The interesting thing is that the convective motion associated with clouds seems to be completely restricted to the belts. Remember I said before that belts was regions of sinking. So this is slightly opposite to what you need in order to create charge separation, which is rising motion. So we have two opposing pieces of evidence going on there. The second is the distribution of chemical traces, and these are those disequilibrium species again. In the upper troposphere, they do seem to follow the classical belt zone pattern. So rising over the zones, sinking over the belts. But down in the deeper atmosphere, and this is sensed via spectroscopy at 5 microns, we seem to see distributions that are the complete opposite of that. In fact, they're enriched over the belts and depleted over the zones, again suggesting upwelling and downwelling in an opposite sense. The next piece of evidence comes from the eddy momentum flux. So this is those little eddies that are cascading their energy upwards to drive the zonal flows. And we've actually been able to observe that in action. We've been able to observe how momentum is being pumped into the eastward jets and that momentum is being removed from the westward jets. But the problem is that if you do the mathematics and you balance the circulation that you need in order to ensure that mass is conserved within that circulation, what you need is flow from the belts into the zones and not from the zones into the belts, as you'd infer from the classical circulation pattern. So another piece of evidence against the classical system. And finally, we said that the winds in the upper troposphere were decaying with altitude, but at some point they have to decay with depth as well. And this is results that came from Juno that use the gravity sensing. So measuring the gravitational components of the gravitational coefficients of Jupiter's gravitational field suggested that the winds had to decay as a function of depth down to a level of about 3,000 kilometers or so, at which point there are no zonal winds in the same way as we see in the upper troposphere. Now, if you have a decay of the jets as a function of depth, that means that your temperature gradients should be the opposite of what you see in the upper troposphere. So there's 4 pieces of compelling evidence there that suggests that we've got our classical picture of belt zone dynamics the wrong way round. How do we reconcile this? Well, with a rather ad hoc picture which puts 2 different styles of circulation cells, one on top of the other. The upper cell is the domain where you have these jets decaying with altitude and you have rising motion over the zones, whereas you have then a deeper cell where you have rising motion in the belts, generating the thunderstorms, belt to zone transport, balancing the eddy momentum flux convergence, and those circulation patterns help us to explain the distribution of the gases that we see. Now, is this picture right? That's a very good question, and it's a question that we're trying our best to resolve at the moment. What we have is lots of pieces of evidence which point towards this type of circulation pattern. And in fact, the interesting fact is that when you do global climate models, numerical simulations of these planetary atmospheres, you actually get a circulation pattern that's more like the deeper cell there than you do of the upper cell. So actually the deeper cell, where you might have ferrule-like circulations accelerating those jet streams, is easier to explain, if you like, than the upper cell in this stack. So the jury is still out on whether this is a realistic picture of the circulation of Jupiter and Saturn. But what's needed is the ability to connect measurements above the clouds to measurements below the clouds. And that is literally the cutting edge of Jupiter and Saturn atmospheric science right now. Now, having looked at the larger scale structure of belts and zones, let's hone in on the smaller scale discrete vortices and storms. And I couldn't resist putting in these images from Juno showing the great red spot of Jupiter, a large swirling anticyclone taken by the visible camera and processed by talented amateur computer scientists and amateur astronomers to create these incredible montages. You can actually see that the red material of the great red spot there, I always like to think of it as an orange haze or filter that's just sitting above deeper churning motions that are down within the ammonia ice cloud deck. So if you somehow blew away that orange haze, what you'd see then would be a swirling white anticyclone down at greater depth. And you can kind of see tendrils of that orangey material being extracted from the great red spot by passing smaller anticyclones there on the right hand side. So this is a very dynamic feature that's always changing. In fact, it's changing so much that if you rewind the clock 40 years back to the Voyager observations in 1979, the great red spot looked very different. It looked much more elongated than we see today in those Juno observations. And in fact, the Hubble Space Telescope has been tracking the changing morphology of the great red spot for many, many years, and has been seeing a continued slow shrinkage in the east-west extent of this feature, raising the prospect that maybe the great red spot may not be around forever, and maybe it will dissipate and potentially be replaced by something else in the coming decades. But for now, it's still present, but it is getting closer and closer to a circular appearance, very different to what we first saw at the beginning of the space age. Now, the vertical structure of these vortices, and I'm not just talking about the great red spot here, there are other swirling anticyclones present within Jupiter's atmosphere that show similar properties. It's just that the great red spot is the most dramatic. Here's a cartoon from Mike Wong and colleagues that suggests what the circulation might be within these vortices. Here in the upper troposphere, you have rising motion above the cloud sheet. This causes the center of the great red spot and these vortices to be very cold, which we observe with ground-based telescopes. The air then sinks around the periphery, leading to warmer temperatures on the edges of the great red spot. Now, again, that's what we typically measure from a spacecraft or a ground-based telescope. But numerical simulations suggest that you've got to have some deeper circulation that is in balance with the motions that we see at the cloud tops. And that would imply that beneath the great red spot is a warmer core, deeper down at greater pressures. And you need that warm core compared to a cold exterior for the thermal wind equation to suggest that winds will decay with depth, because we don't expect those great red spot winds to get faster and faster as we go deeper. In fact, we expect them to decay away. We just don't know how deep the great red spot must ultimately go. So step in the Juno spacecraft again. Here are slices through the atmosphere measured by the microwave instrument on Juno, which show that at the top of the atmosphere, the great red spot is cold, consistent with rising motion and adiabatic expansion. But as you go deeper and deeper, we pass through this thing that we term the vortex midplane, and we get to a regime where the center of the great red spot is actually warmer, denoted by the brighter colors, than the exterior. And that's consistent with winds that decay with height above the midplane and then decay with depth below the midplane. And I hope in that you can see some similarities to what we were talking about with the belt zone structure, which again have decay with height and decay with depth. So these vortices have vertical extension. We don't quite know how vertically extended they are, but we're starting to understand the circulations that underpin them. On an even smaller scale, we have individual discrete plumes that pop up within the cloud deck, bring material up from deeper down below the clouds, and then interact with the prevailing zonal winds to create some incredible patterns. So let's just look at the cartoon on the left-hand side for just a second. The key concept to bear in mind here is that moist air on a giant planet is not naturally buoyant. It's not lighter than the surrounding hydrogen and helium atmosphere. In fact, nothing can be. Hydrogen and helium is the lightest subject. So what you need is some source of energy which starts the rising motion, brings the air up via convergence and ascent to above what's called the level of free convection, at which point, as the water is condensing, it's relinquishing its latent heat, it's warming up the surrounding atmosphere, and it's making it buoyant compared to the natural environment surrounding it. So you have warmer air, buoyant, loaded with vapors that are then condensing, and that initiates this free convection that brings it up towards the upper troposphere. The upper troposphere is stably stratified. It's like a rigid lid. So you've got the plume comes up and hits the rigid lid and starts to expand. As it expands, it adiabatically cools. All those vapors continue to condense, and we get reflective white aerosols as a result. It's cold and reflective, and that's exactly what you see on the right-hand side. You can see the small white spots, which are complexes of convective storms. They're very reflective because of all the condensed vapors forming the aerosols, and they're very cold, which make it dark in the thermal image in the top figure just there. Now, once you've got all this material up in the upper troposphere, it then begins to fall back downwards. You've got downdrafts, you've got precipitation of ammonia snow, or there's a concept out there known as mush balls, which are a blend of water ice and ammonia ice, which then will be falling down through the atmosphere and taking the gases down to deeper levels and potentially passing back into the deep, dry convecting layers to start the whole process all over again and making these plumes somewhat self-sustaining. In fact, they last for several weeks, if not months in some cases, reinforcing themselves and then being blown around by the prevailing zonal flows within Jupiter's atmosphere. So these individual plumes can be understood from the perspective of terrestrial convection, if you like, and lightning and the processes which form cumulonimbus clouds, but they're operating in a very different environment compared to what we're used to. So what are the consequences of all of this? This plume activity, the vortices, and the circulation patterns that we've been talking about. At the beginning, I talked about having discrete cloud decks of water ice, ammonia ice, maybe methane ice on the ice giants, and H2S clouds on the ice giants as well. These should be forming at the level at which the temperature is sufficient for them to start to condense. But as soon as you start mixing everything, what you begin to get are clouds forming in very different regions to where you would expect them to be. Now, this is borne out by the Galileo probe observations. As Galileo probe descended into the Jovian atmosphere, we might have expected to see discrete cloud layers as we did on the left-hand side. Reality was far more complex. The clouds were in very different locations to where we were expecting. Some were very thin, some were thicker, and we suspect this is simply the influence of meteorology and circulation changing the locations of these discrete cloud decks. In addition, spectroscopically, we don't see a pristine ammonia cloud or a pristine methane cloud. What we detect is a broad absorption and scattering properties due to some kind of cloud material present within the upper troposphere. And we have to then try to deduce what that material might be. It's certainly not a pure ice. It's more likely to be a complex mixture of different ices, potentially even coated with that photochemical gunk that's sedimenting down from the upper atmosphere. So the picture of cloud decks is radically altered by the presence of these circulation patterns. There are also unexpected consequences. Back in 2010, one of these types of plumes erupted in the northern mid-latitudes of Saturn, bringing material upwards, then interacting with the zonal winds to create this beautiful snake-like appearance that you see on the top left. Now, all of that energy rising up and hitting the rigid lid of the tropopause was serving as a source of waves. Those waves propagated higher up into the stably stratified middle atmosphere, and they combined in ways that nobody expected to see. This is a thermal image of Saturn taken a few months after the storm erupted in the troposphere. This thermal image is sensitive to altitudes some 300 kilometers above those convective clouds. That bright, hot anticyclone that you can see in the stratosphere just there is some 80 degrees Kelvin warmer than the surroundings. So a storm that happened down at depth within the troposphere radiated waves. The waves somehow interacted with the structure of the stratosphere to create this enormous hot vortex that we nicknamed the beacon. And the beacon was present for 2 to 3 years after the eruption of the storm, and was a dramatic event within the Saturnian atmosphere that we tracked with both Cassini and with ground-based facilities. Finally, the consequence of all of this convective motion, vortices, and storm activity is that if you were an alien civilization looking at our solar system from afar and tracking the light curves of Jupiter and Saturn as they're rotated, you're not resolving any of the detail. You're just looking at the amount of light you get as a different face of Jupiter is looking towards you. It's causing those light curves to meander up and down as a function of the rotation of the planet. This is what we are now beginning to see on a handful of brown dwarfs and extrasolar giant planets. Their light curves show similar modulation. So maybe all of this dramatic dynamics that we see on Jupiter and Saturn is also influencing the light curves on these distant brown dwarfs and exoplanets, which is a nice way of connecting what we're trying to do with the solar system studies to the wider study of atmospheres throughout our galaxy. Finally, let's look at some of the more recent observations of how these planets are changing as a function of time. Now, Saturn was observed by Cassini over the course of 13 years. I mentioned that this was about half of a Saturnian year, which allowed us to track the evolution of temperatures as we went from southern summertime conditions through to northern summertime conditions over the course of half the Saturnian year. And this diagram can show how the stratospheric and tropospheric temperatures evolved to that changing insolation as a function of time. Now, if we zoom in on the equatorial region of that planet, we can actually see that if we subtract away the ambient temperatures, we can see perturbations to the temperature that are changing on even more rapid timescales over the course of just a few years or so. And this is what we term the equatorial oscillation. It's a descending pattern of warm and cold air masses that moves from the upper stratosphere down towards the tropopause. We see that on Jupiter, we see it on Saturn. There's an analogous process on Earth called the quasi-biennial oscillation. And these oscillations require long-term data sets in order to study them. But they appear to be so regular that they're sometimes referred to as the heartbeat of a world. They change with a very regular cycle. Nevertheless, storm activity has been shown to disrupt these regular cycles, and sometimes the pattern can be completely eradicated, but then reformed again later on. And I could give an entire lecture on the processes at work in shaping these equatorial oscillations. Recently, we've been looking at the Jovian equatorial oscillation, and you can see it here from these stratospheric thermal images, where the equator goes from dark to bright to bright to dark over the course of a 30 or 40 year period. In fact, we now know that the periodicity of this oscillation changes with time. Back when we first detected it in the 1980s, the period was between 5 and 6 years. Then in the mid-90s, something happened, a big tropospheric disturbance, which eradicated the pattern. And when it reformed, it was now in a 4-year period. And you can see that the tropospheric meteorology is actually affecting the periodicity of this heartbeat that we have in the upper atmosphere. If we look at the troposphere itself, this is a diagram that shows the cloud colours over a 17-year period. You can see that the equator and the neighbouring north and south equatorial belts, they're not always the same. Sometimes the belts can fade away entirely, looking white in appearance and much more similar to the equatorial zone. The north equatorial belt, you can see it expanding and contracting over the course of time as it changes in its width. We don't truly understand why this is occurring, but observations at the moment are simply trying to characterize the periodicities involved. One of the most dramatic examples of a periodicity within a planetary atmosphere is the periodic cloud clearing events that happen at Jupiter's equator every 6 or 7 years or so. Top left is a thermal infrared image of Jupiter, where dark regions are regions where you've got thick clouds. Now, normally the equator is completely dark. It's completely overlain by those bright, reflective ammonia aerosols which block light from escaping from beneath. But every 6 or 7 years or so, the clouds part and you're able to see down deeper into the atmosphere, as we did in 2007 just there. Now, for some reason, this seems to have a 6 to 7 year period. That's nothing like the 11 to 12 year period of Jupiter going around the sun. It's nothing like the 4-year period of that equatorial oscillation. So trying to understand what's going on here is really challenging and is an active topic of research. The 5 micron radiance can be, you can look at the north-south variation in that 5 micron emission. And here you can actually see the changes to the equatorial belts. North equatorial belt near 10 to 20 north, south equatorial belt near 10 to 20 south. In some epochs, the south equatorial belt can almost disappear completely at 5 microns. And in fact, the visible light image in December 2010 shows a rather unusual structure where that belt is completely hidden by overlying white aerosols. Then in late 2010, early 2011, we started to see massive plumes popping up. Those plumes were bringing up material and creating those little white cloud features that you saw in the earlier slides. Surrounding those cloud features was precipitation. Precipitation was pulling down the aerosols and the gases to deeper levels, and in fact was so powerful that over the course of a few months, all of those white aerosols were removed and the south equatorial belt was back to its normal appearance and back to its normal 5 micron brightness. These changes also have periodicities, 4 to 5 years for the north equatorial belt and something slightly harder to pin down for the south equatorial belt. So there are cycles at work in all the equatorial domains. And if we take a step back and wonder where these cycles are coming from, it's compelling to think about natural cycles within the Earth's own atmosphere, the Earth ocean atmosphere system, I should say. So we have the El Nino effect in the Pacific, we have the North Atlantic Oscillation, the Madden-Julian Oscillation in the Indian Ocean, and also our own quasi-biennial oscillation. These are all driven by interactions between the mean zonal flow within the terrestrial atmosphere and seasonal variability, winds, convective instabilities, driving natural cycles in terrestrial climate systems that we're only beginning to understand in giant planet climate systems. Maybe something in the deep interior of Jupiter and Saturn is controlling those periodicities, waves ringing about within the insides of Jupiter, for example. Maybe there's something about the inhibition of convection. When you have lots of water condensing, it actually stabilizes the water cloud layer. Maybe that layer is so strong that it takes a buildup of convective potential energy before it's overcome and you get this relinquishing of energy that drives the large scale changes. Or maybe some of these changes are somehow connected to changes in the magnetosphere, where currents are flowing in the high atmosphere and potentially influencing circulation patterns in the upper atmosphere. We just don't know. All we know today is that there are cycles of activity in the giant planets which have a regular period. They can be disrupted by meteorology, and we'd like to better understand what's going on. With that in mind, let's look to the future. How might we advance our understanding of the giant planets Jupiter and Saturn? Well, Juno has been the real workhorse for the past 5 years, exploring the hidden depths of the atmosphere of Jupiter. And there's a series of science and nature covers here which attest to the success of that mission. In the last few days, it's been announced that the Juno mission will continue beyond its planned end of mission in July of 2021. It will actually continue, hopefully, all the way through to 2025, depending on the availability of resources on the spacecraft, and will continue to explore the deep atmosphere of the giant planet. This year, we have the highly anticipated launch of the James Webb Space Telescope, an infrared observatory that will observe the distant universe, but also spend time looking at targets within our solar system. I've used an example of Uranus on the right-hand side here, but it will also be looking at Jupiter, Saturn, Uranus and Neptune, using its suite of infrared instrumentation in the next couple of years or so, with a sensitivity that is simply unprecedented. So we're hoping to understand more about these atmospheric cycles and giant planet meteorology from the James Webb Space Telescope. Looking further ahead, in 2022, we're hoping to launch an ambitious European mission to the Jovian system. JUICE is the Jupiter Icy Moons Explorer. It's the first European mission to Jupiter. It is also going to be the first ever spacecraft to go into orbit around an icy world. That is the largest moon in our solar system, Ganymede. So JUICE will spend 3 years exploring Jupiter and flying past each of its moons before finally ending up in orbit around Ganymede. It will launch next year in 2022, arrive in 2029 for a 4-year mission taking us into the early 2030s. The early 2030s could also be the time when we finally get another mission out to the Uranus and Neptune system, shown here as a cartoon to reveal the richness of the planets themselves and the satellites and ring systems surrounding the ice giants. And we're hoping that everything we've learned from Galileo, from Juno and Cassini can ultimately be applied to understanding the ice giant worlds as well. So the next couple of decades could be particularly exciting for our exploration of the outer solar system. So let's finish with some perspectives on what we've learned about the atmospheres and interiors of the giant planets over the past few decades. We've seen that atmospheres are influenced by a dramatic and intricate coupling between dynamics, chemistry, cloud formation processes, and local scale meteorology. And these are then modulated by both seasonal changes and by natural oscillations in their climate systems, which we're only starting to observe and to understand. The impact of all of this coupling of dynamics, chemistry, and cloud formation is that clouds and gases are rarely where you expect to see them from a remote sensing perspective. And that remote sensing itself provides degenerate solutions. So it takes an army of people taking the data, modeling the spectra, and also trying to interpret the results of that spectral modeling to make sense of what we're seeing within these giant planets. An interesting connection to the expanding field of extrasolar planets and brown dwarfs is that all of the dramatic activity we see on Jupiter and Saturn would be modulating their rotational light curves, so that what we learn about the dynamics on these worlds could be of relevance to interpreting the light curves that we see from these distant extrasolar planets. I'd like to remind you that it's not all about spacecraft visiting these worlds. We do also need ground-based facilities to provide spectral context, temporal context to what we see with these short-lived spacecraft missions, and they're just as valuable when trying to interpret what's going on with the giant planets. But the coming decade does blend these two things together: the Juno extension, the JWST launch, the JUICE launch, and the rise of the extremely large telescopes. Those are 30 to 40 meter diameter class, which will really revolutionize our ability to explore these astrophysical objects. With that, I'd like to thank you for your attention. I look forward to speaking to participants on the Winter School live session later in this month. And thank you very much for listening to this lecture.